So hi, I'm Holger. I'm an applied research scientist at NVIDIA, mainly working on federated learning. So I wanted to give you an introduction, federated learning, mainly with a focus on medical imaging and healthcare. So what is federated learning? Typically, we talk about federated learning as some form of machine or deep learning or computation on decentralized data. It enables devices, those can live on the edge, it could be other devices, to do state-of-the-art machine learning without a need to centralize the data. And that gives us some inbuilt privacy by design. So the reason for doing this, of course, is that we typically assume that with more available data to machine learning models, we can achieve better, more performant, more robust models. And this has been shown many times. So typically we see in computer vision applications this kind of logarithmic relationship between the data set size and the model accuracy. So typically this means that you need a lot more data in order to get yes?
Really quickly to interrupt you, I don't think we're seeing your screen, or it's sharing the wrong screen on our end, because we see your PowerPoint not full screened, and you're still on the first slide on our side. So I think maybe it's sharing the wrong screen if you have two monitors up or something.
Yeah, I just went into presentation mode. Doesn't that normally work?
I think so, but we still see slide number 1, and it's in the sort of minimized view for that. So I don't know why.
Can you see this now?
There we go. Now I'm seeing it. Can everyone else see that? I got yes. Yeah. Yes is in chat. So it looks like you're good now.
Sorry. Okay, sorry about that.
No problem.
So yeah, I was talking about this, what is federated learning? So it's mainly about doing computation, machine learning on decentralized data. And of course, with the goal in mind that having more accessible data to the model, we can achieve more robust, more generalizable models. And I was showing this relationship graph that shows that you typically need much more data in order to get a significant improvement in your AI model in terms of accuracy. So, however, especially in the medical setting, creating these large centralized data sets is very challenging. Private data can typically not shared easily, especially patient data. Anonymization is sometimes not effective. You know, we have the examples of brain imaging data being used to identify a person based on the structures in the brain. For example, there's a paper down here mentioned doing that. At the same time, you know, preparing data sets is very costly. So for hospitals or research institutions, data is an asset. So they don't necessarily want to share the data in its raw format. And of course, all the bureaucracy, regularization of data sharing is very complex, especially in healthcare. So what if we can still learn models without sharing the data? So the assumption here is that we can actually train models together by sharing model parameters, but not raw data. And this is exactly what federated learning is doing. It's some way of training models on local data and updating model parameters and aggregating in them in some way to update a jointly trained model. There are different ways of doing this. Like you could do this kind of cyclical learning approach where a hospital is training a model and then it's passing it on to the next hospital and to the next, and kind of do the cyclic fine tuning, which has been shown some success in some applications. Or we can do this in parallel, where we train on several hospitals in parallel and then aggregate the parameters in some form in a centralized node. There are different ways of implementing this in practice. You know, we have to do communication over the internet, basically. And for doing that, you can have these client-server architectures where everyone is communicating with a central server, or you could have peer-to-peer architectures where sites are communicating directly with each other, or you can have hybrid structures. So there's a lot of complexity, but also a lot of flexibility in how you can implement this. In federated learning, of course, originally this came out of Google research, and they used it for doing training on edge devices. So this is typically called in the mobile sector, it's called a cross-device setting for federated learning. And there you would have sometimes millions of users. Typically, they don't know each other. Sometimes not all users are available, right? So typically the training algorithm has to select from a pool of users to update the global model. And also users could be, during the training of the model, could be changing the data. So this is a bit more of a dynamic situation. But at the same time, it's massively distributed, and typically the devices don't have a lot of computational power. So in contrast, in typical healthcare applications, you typically have institutions that have a lot of data. They typically have dedicated computational resources. They might have a GPU cluster or something on premise where they can do the training. So this is referred to as the cross-silo setting. And yeah, this can start from tens to hundreds of clients. But at the same time, they have a stable data set. Typically, the users know each other. You know, the hospitals do sign some sort of agreement to join this collaboration. And we can typically train stronger models, or like larger models, because of the dedicated computational resources. So if you're more interested in the kind of the general motivation for federated learning in the healthcare sector, we actually wrote this paper on the future of digital health with federated learning. And that really goes into all the details about the benefits that FL could give the healthcare sectors, going from clinicians to patients, to researchers, to the hospitals and practices, and even scanner manufacturers, for example. So here, I also want to show some of the federated learning application settings. So there are different types people typically are interested in. The most common, I would say, sorry about it, is the horizontal federated learning, also called homogeneous federated learning. And here the data is split by examples. So typically each hospital would have the same kind of data, but for different patients. So each hospital, there's at least no known overlap between patients' data at the different hospitals. So let's say they all have a CT scan, and the goal is to train a classification or segmentation model. But all the data is from different patients at different hospitals. In contrast, the vertical federated learning, or heterogeneous federated learning, is where the data is split by features. So that might be, if we go in the healthcare sector, it might be a hospital that has the imaging data of a patient, but then the same patient has also blood test data that is in a pharmacy, for example. So then you could find this kind of intersection of corresponding patient data across different institutes to train more informed models. Similarly, a different application would be federated transfer learning, where maybe you just have a small amount of common data to train an FL model, and then institutes are using large local data to then fine-tune their models. Or you could have multitask settings where maybe hospitals are interested in segmenting different organs from the same image modality. But the model could still benefit from collaborating training jointly because there are like shareable features within these different images. At the same time, you could become very complex in building different network architectures for each client, maybe having client-specific hardware considerations in mind. And finally, as another example, there could be a federated evaluation where you maybe are not interested in actually training the model, but just using your federation to evaluate models on a large scale. Okay, so some of the data and compute challenges in federated learning. First of all, there's this question about, do you want to train a globally optimal model so that's working well across all your clients, or you could have locally optimized or personalized models. Of course, that goal, if you decide on that before starting the federated learning, that might influence your algorithmic design and how to train these models. And of course, with having the data now separated at different locations, data disparity across the sites becomes a larger problem, right? The data number, appearance could be different, imaging protocols, patient populations will be different at each site. Annotation numbers can be different. Sometimes the annotation standard is quite different. So that's all within the kind of the non-IID setting of the data. And we can see this here as an example from one study we did on breast mammography, where we can see a lot of differences in the intensity profile across the different sites. And then also works that study these federated learning settings on IID data or non-IID data. We can typically see that there will be this kind of client drift or divergence as you train with clients that have a very different data distributions. So there are ongoing research that tries to mitigate this problem, like FedProx, FedMA, FedOpt is some of the recent works, and they typically are around client regularization, trying to avoid this drift of the clients or this divergence of the clients, or modifying the aggregation functions that update a global model to be more robust. And of course, there are also hardware considerations that you might want to include in your algorithmic design. Like, there might be some very clients with a strong hardware, but some have low-end GPUs, so that you run into this straggler problem where the fast clients are waiting for the slowest one to then proceed to the next round of training. So there are these kind of challenges that currently need to be solved in federated learning. Okay, next I wanted to talk about just show you some of the use cases or studies that we did so far at NVIDIA around federated learning. So we started with brain tumor segmentation, a collaboration with KCL, where the focus was really about understanding how differential privacy impacts the federated learning performance. I will talk about this later on a little bit. And then we did a couple of real-world studies around breast mammography, prostate segmentation, and pancreas segmentation. And you can see that these are all collaborative efforts, right? So the federated learning is really a way for different institutions to join together. So for mammography, we had in the Americas 7 institutes, and then this is in North America. This is 2 sites in Taiwan and in Japan working together without having to share the data, but training models. And then most recently, we worked with over 20 different sites across the globe on chest X-ray and electronic medical record data to do COVID image classification. And in this setting, mostly we use this server client approach for federated learning. So I just wanted to go through that quickly again, so everyone is on the same page. So the idea is here that hospitals keep the data private on premise, and they have some training resource here to train a model. So first we initialize the model on a global server. This is distributed to all the clients together with some training instructions, and they update their local model and send an update of the model parameters to the server. And that typically, in the simplest form, we apply a weighted aggregation of the updates on the server to update the global model. Of course, we can also add additional privacy preserving techniques. You know, there is theoretical potential for data leakage when you send model updates, even though you don't send the raw data. So we can add additional differential privacy or encryption techniques to avoid, even if there's a very small theoretical chance of data leakage. So typically, the benefits that you get is something like this. So here we have this pancreas segmentation task where there are two clients in Japan and Taiwan, and they have slightly different tasks in their annotations in the data set. One has 3 classes: pancreas, background pancreas and tumor, and the other one has only healthy pancreas with background and foreground pancreas being the annotations. So if you train your model on data that always includes a tumor, of course it's becoming somewhat too sensitive, and even predicts here a tumor on a case that is a healthy patient. So by training through federated learning to train this model together, so we get a global model that is robust to these kind of false positive segmentation. So here we just get the healthy pancreas segmented. And the same is true the other way around. There we go. Here, if the client 1, which only has healthy pancreas, of course, the model trained just on the client 1 data has no knowledge of pancreatic tumors, so it misses this region completely. While the model that's trained jointly on this larger combined data set, even so without sharing any of the data, right? It's just made visually aware of the data through federated learning. It can learn the tumor segmentation quite well. Okay, so with that, I wanted to go to this larger study that we did with 20 sites across the globe on predicting the need for oxygen treatment of a patient arriving in the emergency room with symptoms of COVID. So the input to the model here is an X-ray and certain common blood tests and lab values that they typically acquire when the patient is arriving at a hospital. And then the model is combining these features to predict the risk for oxygen treatment. Like, is there a chance that this patient needs to go on a ventilator in the next 24 hours? The results were just published last week in Nature Medicine, so you can also check that out. And what we saw is really that this global model achieves a much more robust performance on average across the different sites. So in blue, we see model performances on their own test data when they just train with their own training data. This is ordered by size. So the largest client is number 1, smallest one is number 20. So you can see, like, even the small site, they don't have even enough data to train a robust model on their own data. So they get a huge boost on the local test data. But interestingly, if you look at the performance of the global model across all the test data across the 20 sites, then we get a much larger boost in generalizability compared to any of the models trained on their own local data alone. And then we took that global model and tested it on another 3 independent sites for predicting the mechanical ventilation. And there we achieved a very good sensitivity of 95% and 88% specificity. So typically this means that the model is erring on the kind of conservative side, so it would rather predict somebody needed a ventilation rather than not. But it really shows that these models trained through federated learning are robust to even unseen data in this setting. Or I should say unseen data from a different hospital domain. Okay, so then I also want to introduce some of the research works we're doing. So semi-supervised federated learning is another topic where one client could have a lot of data, but maybe there are no annotations. So we can show that you can use self-supervised training techniques on those clients that don't have annotated data, and then still help building more robust global models in federated learning. And as I said, this simple averaging of the global model might be not the optimal way of aggregating these models from different clients, because typically these aggregation weights are based on the client dataset sizes, but that might not be optimal, right? It might not capture the amount of information that's in that data from the client. So here we try to learn that automatically in a data-driven way, and we model the aggregation weights using a Dirichlet function. So you can see that during different rounds of the federated learning, these aggregation weights are being learned and they converge to a certain setting. So you would kind of interpret as that client 1 in this setting has the most informative data, so it gets the highest weight, and that achieves a better performance on average. Yeah, here are some examples. And the federated averaging is the baseline, where you just weight based on the client dataset sizes, and the AUTO-FEDAVG, where we learn these aggregation weights, results in a more true segmentation of this COVID lesion here in a CT scan, or it reduces the false positive region here. So as I said earlier, there's also this option to do personalization. So here we show that models trained locally achieve this testing performance in blue. In green, that's the performance of the federated learned models. And then if you do some further fine tuning of these models on the local client data set, you can get even a higher boost in performance. We also explored personalization through model architectures. So here we utilize a neural architecture search technique called the SuperNet training. The SuperNet can be trained in a federated learn setting. So here we have like a rough 3D unit architecture, but certain layers are searchable, so there are different candidates. And then we can actually find the most optimal network architecture for each of the client by optimizing this pathway through the candidate layers. This is our work that will be presented at MICAI 2021 next week. Okay, so finally, I mentioned it earlier already, some of the privacy aspects of federated learning. I mean, there are works on model inversion, so you can potentially leak some data information from trained models Equally, in federated learning, of course, the question is like, can you get any information from the gradients that being exchanged? There's some work that shows that there is a theoretical possibility of recovering some information about the training data. Also, you could use like some GAN approaches to try to reconstruct images. So early on, we had this in mind in developing the federated learning tools. So this work is looking into how we can use differential privacy techniques like partial model sharing or gradient clipping, and how that impacts the performance. So that you can see that the pure FL model in magenta is on top here in terms of the DICE performance. But with some privacy preserving techniques, you can get a pretty similar performance, but you're reducing the chance of any data leakage. And this is seen here, visualizing some of the trained models by inverting images using based on the trained models. So in the raw FL scenario, you see these inversions somehow capture more detail in the image, while models that are trained using differential privacy much less able to preserve these techniques, so that these details in the images. So typically indicates that a model is memorizing less of the training data. So that just brings me to the point that in the security in federated learning is another very important topic, and security is always multi-layered. So we have authentication, so public key infrastructure, secure communications channels through SSL typically, and then even on top of that, we typically apply techniques like differential privacy. We could do homomorphic encryption, where the updates from the clients are being encrypted and the server does the aggregation in an encrypted space, so it never sees the raw model updates. Or you can do federated learning using multi-party computation. Okay, so here's our working group led by Jayashri, Danielle, and me. We are trying to build FL examples using MONAI, reusable components, and work on standardization. So if you're interested to contribute, please contact me. And here, I just want to show the tutorials that are currently available in MONAI. We have 2 federated learning systems covered here, NVFlare from NVIDIA and Substra from Okin. Both of them use 3D segmentation trainers based on MONAI to do the model training, and then use the specific infrastructure to do the communication across clients and server. And also, if you're interested in this topic at MICAI, the second workshop day next week, there will be a dedicated workshop that we are organizing around distributed and collaborative learning, which will cover a lot of these, the new research in federated learning and in medical imaging. So with that, I would like to thank you for your attention.
Great. Thanks, Holger. So I know a lot of people have been asking questions in both the Zoom and Discord. If you asked your question in Zoom, I encourage you to post it over on Discord, because we won't have time to go through many of them, but we can always continue the conversation over there. It's a little easier to kind of track and thread things on Discord. So if you did post it in Zoom, try to get it over in Discord. But I'm going to start, Holger. I think we can get through maybe 2 or 3 questions. So first question. For some NLP work, we have had to consider our models as containing PHI. I wonder if an ML model might have a similar issue. So just generally, I guess, PHI, and I think you already covered a little bit about that, but any additional sort of thoughts on that?
Yeah, I think that, so this potential for data leakage, I think it's definitely dependent on the tasks that you're trying to solve. So some images, like let's say abdominal CT, they typically have less patient identifiable information in them. So I would say, depending on the task, what kind of data you work off, you have to keep this differential privacy aspect, give a higher consideration to this differential privacy aspect. So you might want to apply stronger privacy guarantees when you work with NLP data, of course. For example, that might include patient names or something like that, right? So that's definitely something that's a more stringent scenario, I think, than a lot of the imaging data examples that I talked about.
Yeah, that makes sense. Okay, so next question. How do you standardize the way models are trained at the edge for them to be aggregated and under different environments? I think you mostly talked about that through your presentation. I think that was really early on. But anything you wanted to mention about sort of the standardization of the way things are trained at the edge?
So yeah, in the easiest way, you have the same model being trained on the different clients, right? And then but there's a lot of flexibility. You can say, like, maybe I just want to train the encoder part of your model jointly, and then have local classification layers for each client side. So this is the kind of the flexibility that then you can get to build personalized models out of the federation.
Yeah.
So this is all very flexible.
Okay, great. Next question. How does one aggregate models in vertical FL, where the features are not the same across the sites?
Yeah, so there's a linkage problem in vertical FL, right? You have to first figure out which features correspond. So there's a lot of work in the encryption cryptography solutions that allow you to compute the matching features in a secure way. So you do that as a kind of an additional step to first build up your data set in this federation, and then you train your models, also typically in an encrypted fashion. So that, of course, makes it more complicated.
Yeah.
But it's a very interesting use case, I would say. Yeah.
Okay, so we'll go through two more. I know we're right at the end of time, but there was a lot of questions here. So let's see, in terms of actually setting up a network with an array of clinical partners, what would be the go-to solution to use alongside MONAI? They've been seeing different open source frameworks like Vantage 6 or PyGrid, but one of their biggest hurdles has been bypassing things like firewalls. Any thoughts on that sort of infrastructure setup?
Yeah, so with again, I encourage you to look at the tutorials that we provided in MONAI, right? So we have a tutorial around NVFlare, which comes from NVIDIA, so I'm most familiar with that. And there we actually have a provisioning setup tool that allows you to set up exactly the authentication for different participating sites and kind of what port numbers should be made available. So using that, we as I said, like we were able to do a study like the Nature Medicine study with 20 sites across the globe without too much problems on the IT side, right? We had like this provisioning done once, and then hospitals were able to join the federated learn the server using their what we call startup kits. So in the example, we have one example that has a set of prepared startup kits to run on localhost for simulation to kind of do research. And then there's another example that does show you how to use Dockerized environments that are then more easily to deploy at different sites and how to do the provisioning.
Yeah. That's great. Yeah, so just kind of to add on to that, I know that we have both the ClaraTrain examples NVIDIA GitHub repo that has some federated learning specific notebooks. We also have the NVFlare example in the MONAI repo that Holger pointed out right at the very end, along with the Substra one. Someone did ask what federated backends would be implemented in MONAI, things like OpenFL and Intel or any custom community ones. Did you want to sort of talk about how we're engaging on the MONAI side of things with the FL community?
Yeah, I mean, this is really something for a topic for the working group, I think. Like we of course, we want to use MONAI as a way to bring people together. So our first approach was to build like examples of how to use different frameworks with custom MONAI components. So we currently have NVFlayer and Substra using custom MONAI trainers, but use those NVFlayer or Substra frameworks for the FL communication. Of course, the aim is to have more examples down the road. Maybe OpenFL can be one of those in the future. And as I said, we hope that at some point we will build a standard that maybe allows different frameworks to talk to each other.
Yeah, definitely. And I to add on to that, we've been working with some of the OpenMind people, Andrew and Hema over at OpenMind, talking to them about how we might be able to get some of their examples into the MONAI repo and kind of expand on sort of the portfolio of federated learning platforms we have and how they integrate with MONAI examples and tutorials. So we'll go with one last question and then we'll go over to Andres. So the last question I have here would be, any idea on how to get FL models approved by FDA as the performance of the network changes over time? So I guess generally with FDA approval and FL models, is there any sort of advice or thoughts you've had to go through with your current examples?
Yeah, so typically we go to, I think you have to go the route of doing then a prospective study of the model. I mean, it's not different to other AI models, I would say, because what we end up after federated learning, you end up with a global model that you might want to go through FDA approval, or you could have a set of different models, but all of them have to go through this kind of rigorous testing after you trained it to meet the FDA requirements.
Yeah. So actually, I'm going to do one more question. I know that I said the other one was the last one, but this person asked, in what capacity can we contribute to this working group? And I think kind of your answer will kind of generally apply to a lot of the working groups, but how can someone give you their feedback and work with you to kind of get their input into the working group?
Yeah, so feel free to email me directly. We can discuss that, of course. One thing that we're currently doing is to prepare a survey around the needs for federated learning and kind of what aspects the community is most interested in. So hopefully, Michael, we can maybe distribute that with the participant list here at some point in the near future. And then that would be a very interesting way of collecting your feedback.
Yeah, definitely. Okay, great, Holger. There's still some other topics and questions that are there in Discord. So if you get a chance, hop over there. I think there's still some other ones that we didn't get to, but that was a great presentation and a lot of great discussion came from that. So thank you.
No worries. Thank you very much.